There's a brand new handout on your tables. It is called something like Practice Problems for MAT 202. Go ahead and grab that packet. I used to hand out a practice test before each of the tests. I decided instead of keeping them as separate documents, I would just make them one big document. So that right there is the set of all the practice tests that I used to hand out separately. If you want to study for a quiz or a test, you got to make sure you know how to read this first page, the chart there. Today we are covering lesson number 2, and if you look in the first column, you'll find in bold a number 2, class number 2. And if you go just to the right of that, you will see problems 1 and 4E and 15A. Everybody with me? Right next to the big 2. Those are the problems in this packet that are relevant to today's class. You want to practice stuff for today, you look at in this packet, problem 1, problem 4E, problem 15A. Okay? Thank you. The other new thing on your table, which you will want to grab one of, is the Math Studio bookmark. This tells you exactly when there will be a math faculty member on duty to answer all of your questions right across the hallway. So grab one of those. Feel free to take a photo of it if that's more convenient for you. Okay, so before we jump in with the math for today, I just want to make you aware of a couple of resources. This is our Moodle page. If I just want to point to 2 things for today. The very bottom link here says 202 Packet 1 updated January 27. That was Wednesday, and this is a PDF. And if you click on that link, you'll open up this PDF, which is just a copy of the big packet that you have in front of you, but with the stuff that I wrote on the smartboard on Wednesday. And so you should know that you don't need to frantically copy down anything that I write. You will always have a digital copy of everything that I write in full color up on Moodle. Typically, I'm not going to do this after every class. I'll do it after every Friday's class, so once a week. That's just to save me some time. But if you want it more often than that, send me an email and I can make a PDF for you and email it back to you. All right? So if you ever miss a class, this is not a good substitute, but it's the best we can do, right? So just know that that's always there for you. The other resource I wanted to point to on our Moodle page is this link that says playlist of class YouTube videos. I record all of my videos and I post them publicly on YouTube. So if you click on that link, if you click on this playlist link, you will find a very short playlist with only one video in it. This is the one from the other day, and we'll play a small clip of this now. So you can relive the magic of Wednesday's class, just like that. This is going to blow up on YouTube now that you guys are aware of it. We've got one view, but that's just going to grow and grow and grow. All right. So again, if you miss a class, this is not a substitute, but it's something. But even if you're here in class and you want to hear something, again, just go check it out. It's always going to be there. I will upload those shortly after class, sometimes during class. So they will be there very soon after each class. Any questions on any of those resources? Okay, so we'll start most classes by taking a quick look at our calendar. This is on the back of your syllabus, but you don't need to pull it out. Today, January 29, is class number 2. We're going to review the definite integral, which is, I think, four sections in chapter 5. This is our second and final official review day, and then we start chapter 6, which we are calling new, although some of it will be familiar to some of you. So we begin here on, one other thing in the calendar. Project 1 was assigned last class. It is due on February 3rd. Wednesday coming up is the due date for the first project. Again, you're welcome to work with each other and anybody else. Just credit whoever you work with. You are encouraged to work with other folks. Okay, so here we are on page 22. And we'll jump up here at the top. Our daily summary. In this class, we review the definite integral and the first part of the fundamental theorem of calculus. We also explore some contextual interpretations of the definite integral. Jumping down to number 1, this says let's find the area between the curve y equals sine x and the x-axis for 0 less than or equal to x less than or equal to 2 pi. At the end, we'll use technology to help us, but we'll start by sketching a picture below. The sine curve, I'm just going to label the common multiples of pi here. These are important ones for the sine curve, right? So we'll label those. Using the word start in quotations, does the sine curve start at the top on the y-axis, in the middle, or at the bottom? Sine curve starts in the middle, right? Right there at the origin, and then goes up. So don't worry too much about accuracy, just a very quick, very rough sketch. We're on page 22, but not in this, in the big packet from the other day. Everybody with us? 22 of the big packet from the other day. Okay, so looking for the area between the curve and the x-axis. So I'm just going to shade it in here. It's this hump and this hump, yeah? Okay, so at the end of last semester, at the end of your Calculus 1 course, I think that you saw this symbol right here and started to talk about how we just use that symbol to represent area. So this hopefully will be a reminder of some of our syntax. The 0 and the 2 pi go on this funny looking S symbol, 0 to 2 pi. And then the thing you are finding the area of, that's the sine of x. I'm going to put another symbol over here. It's mandatory. Don't worry about it at this moment, but we'll explain it soon. And so that seems like the right thing to do. That seems to represent the area. That's how we defined that symbol. But the problem is that this symbol actually represents a signed area, an area with positives and with negatives. And technically, that symbol thinks that anything above the x-axis represents a positive area and anything below the x-axis represents a negative area. And if I somehow were able to do this calculation, which we don't have the tools like to do it algebraically, but we'll use the calculator in a minute, what would I get? You're going to get 0, which is not the answer to my problem. So how about instead of doing it that way, let's go between 0 and pi. And then we'll just use some symmetry and double this answer at the end. Is that fair? So a 2 times in the front will give us our actual answer to this problem, the actual area. Okay, we're going to do a quick thing on the calculator. If you have a calculator that can do this, then you can take it out. If not, don't sweat it. I don't need you to have one of these devices in class. If you have an app on your smartphone, that's cool too. I want you to be able to do this kind of calculation while you're doing homework, but that could mean on Wolfram Alpha or really anything else that has this technology. So for me, in order to get my notation or my syntax, I guess, inside of on this calculator, I go into math, and then I scroll down. I think it's number 9, but I'm looking for something that says FNINT. Now, I don't have the most updated operating system on this emulator. Some of you guys might just have something fancy which looks like that integral symbol. So for me, it's going to look like this. I'm going to type in my function, which is sine of x. Close those parentheses. I'm putting a comma x, which is my variable. Comma 0 is that lower limit, and comma pi is the upper limit. So that's what mine is supposed to look like. If you've got one of the fancy newer operating systems, you want it to look like this here, where it just looks like the symbols. So just use your arrows to move around the screen appropriately. And we get 2. Yeah, make sure you're in radians. All of calculus is in radians unless specified otherwise. I'm always shocked when I get a nice number for this problem. Just completely baffles me that the area under that curve has to do with like running around a circle, and circles have to do with pi, and pi is an irrational number. I'm just always surprised that that's a nice number. But it is. So the integral here is 2, and so then we're just going to double that and get our final answer. Other folks able to either get it that way or the fancy syntax way? So 2 times 2, and the total area there is 4. Any questions on that? Yes.
Just a quick question regarding calculator. I accidentally put in as the upper bound, so the 2 pi, and it gave me really close to 0.
Yeah, that's a great question. So if I ask it to do this calculation, so I think you're telling us that you went 0 to 2 pi, and we had said we expected the answer to be 0. Let's see what my calculator does. So I got 0. You got something very close to 0. Right, which is very close to 0. So in a couple of classes, we will have a way to do this problem algebraically and get the absolute exact right answer. At the moment, or in a moment, we're going to talk about how the calculator is approximating that area by doing a bunch of rectangles.
Oh,
And so it's got a little bit of rounding error here and there that makes it so it's not quite 0, but rather 10 to the negative 8. Yeah. Okay, so moving on here. Number 2. Again, supposed to be a little bit of a review. Suppose you have a continuous function f of t, which is over here. At the moment, just to make life easier, we'll assume that it's non-negative. And we're looking for an estimate of the area under the function between x equals a and x equals b. Doesn't say it there, but above the x-axis is what we're after. So this space bounded in there, that's what we're looking for. Everybody okay with that? All of this is what we're trying to find the area of. And so I think at the end of your last calculus class, you talked about chopping that region up into a bunch of rectangles. And so you would take your x interval and you'd cut it into a bunch of evenly spaced pieces. And then you would draw some rectangles. Now, for example, I could look in this bad color there. I could look in this region here, and I could draw a rectangle based on the height of the curve in that region. Now, that's an infinite number of points in that region. Let's just pick the right-hand point. I go all the way up to the curve based on the right-hand point. I go to the left, I drop straight down, and there's one rectangle, which is an over approximation. It's an overestimate. That's okay. And then we could go to the next interval, this one here in red. And again, let's just pick the right-hand point every time. So from the right-hand point, you go up to the curve, over to the left, straight down. And that's an under approximation. And you just keep doing this all the way to the right. I'll draw the last one in blue, something like that. And you add up the areas of all those rectangles, and you've got yourself an estimate for the true area under the curve. And the reason we use rectangles is because we know how to find the area of a rectangle. It's one of the few things we know how to find the area of, right? Length times width or base times height. I made a little mistake here. I put distance. I meant to put area. Can you guys cross off the word distance there? Change it to area. And so for my green rectangle here, the base of this is just this little horizontal length, right? And the horizontal length is the same all the way through. I'm calling it delta t just for convenience sake. So that's a delta t down there is the width. And then the height, well, we decided to make the height based on t1, right? So whatever the function is at t1, that's the height. So f of t1 is the height of that green rectangle. And so I'm going to circle in green. Delta t times f of t1 is the area of that green rectangle. And then the red rectangle, it's another delta t for the base or the width. And then the height of that guy is f of what number? F of t2, picking the right-hand interval, right-hand endpoint. And so delta t f of t2 is the height, is the area of that red rectangle. And you just go all the way to the end and you add them up. And we're saying that's approximately the area. We can abbreviate stuff using sigma notation. I'm going to write it. I'm not going to stress about it too much. But sigma, remember, capital sigma is that guy, looks sort of like an S. The basic pattern for all of these things that I've started to circle is delta t times f of t something, yeah? The only thing that changes is that something, that little subscript. So how about we just copy it as it is, delta t f of t something, and then we're going to put a something in there. How about a k? Use any letter you want. I said k and then I wrote an I. Let's try that. Okay. And then the only other thing we have to do is tell folks reading this, what does k start at? What number does k start at? And what number does k end at? And so for this bottom row of stuff we've started to circle, what's the smallest k value? There's 1, so we'll just put down here start at k equals 1 and go all the way until what's the last k value is n. And so that's our shorthand way of writing that big sum out. Okay? We're not going to do too much with summation notation, but it is useful sometimes. Okay, when you're ready, we're moving to the next page. There's a very fancy picture that's supposed to illustrate something. The more rectangles, the better, yeah? Yeah. So by using more and more rectangles, you have less and less error in approximating the true area, and so that's what's written out here. N in these problems represents the number of rectangles. As N increases, the area of the rectangles approaches the exact area under the curve. And so that allows us to write this very fancy and very symbol heavy actual definition of the area under a curve. This piece right here is exactly the sigma thing that we just wrote. We use K, it was I here. And then limit as n goes to infinity, remember n is representing the number of rectangles. So if you can have infinitely many rectangles, which we can't, but if you can approach, that's what the limit does, then we're going to define that thing to be the true area. That's what area means. Okay, and then again, in your Calc 1 class, you just use this symbol because you didn't feel like writing all of that. That's all. So that symbol with the curvy looking S thing just represents the area under a curve. Yes, David.
So my correct thinking essentially matter where you start.
It doesn't matter where we start the I, meaning like I equals 1 versus something different. So I think it's important that we use that little subscript I to represent the reality, which is written out here. The starting at 0 is okay as long as you chop off one, like you're bringing in one rectangle in the beginning, you better chop one at the end. So the limit, so I mean, you couldn't start at T2, for example, because then you'd just be missing some stuff that you'll never have an opportunity to get. So the limit is really not about the starting value. It's really not about what's happening here, whether it's 0 or 1. It's really about, okay, don't use 3 rectangles or 5, use a million, use a billion, use even more. Yeah.
Doesn't seem like you are too
Mhm.
So what's the point? So small. No, because
Mhm. It's true. I think that we could get away with not using that first rectangle, and if we use or the first 17 rectangles, if you have enough rectangles up there, then the first 17 of them contribute hardly anything because they're razor thin, right? It's really easy to just write this pattern, and so this is a choice of convenience, not a choice of here's how we're actually going to calculate the areas. Is that fair? No. Good questions. Okay, so then the next thing is actually doing some calculations. So right here is something called the fundamental theorem of calculus part 1. It says if f prime is continuous on a closed interval, and you want to find the area under a curve, that's all that this symbol means, area under a curve, the area under the derivative curve. It turns out that's just equal to the original function, not the derivative, but the original function evaluated at the top number minus the original function evaluated at the bottom number. And so in English, it says the definite integral, that's that symbol, of a rate of change is your derivative, is the total change, or the actual change in the function. Let's see it in play in this picture here. The graph of f prime is given right there. Part A says we're going to find the integral from 0 to 4 of f prime of t dt as accurately as possible. So that symbol we know represents area. So we're just going to briefly shade in the area that we're looking for. 0 to 4 between the curve, which happens to be piecewise linear, and the x-axis. So this region right here is one of them. Next one is this down here. It's always between the curve and the x-axis. And then going out to 4, this one here. Lucky for us, those are areas that are easy to find because there's no curves in this picture. So let's go ahead and find those areas. This is the derivative that's pictured here. Okay, so let's find these areas here. The first triangle, what's the area? 1 times 2 and half of that. I think that's right. That's a 1. And then blue, 2 and 1. That's another, whoops. That's another 1 down there. And then, so I'm just writing areas and then we'll handle the negativity. Great question. And then the area of the little red guy, probably a half, right? Okay. So if the question said find the total area, the answer would be 2.5, adding them all up. But that's not what this question says. This question says find the integral. And we know that the integral represents a signed area. So we do have to calculate that this is really a -1 here. So my answer for this guy, it's the +1 in green, -1 in blue, +0.5 because the half is above the x-axis. So that integral is a half.
So wait, one more time. Explain why. What's the difference between calculating them as absolutes or
so the question that we answered first said find the area. And area is always a positive thing. We had to do a little bit of finagling because the calculator was going to cancel these areas out if we just asked it to find the whole integral from 0 to 2 pi. Area means everything's positive. But the symbol, that integral symbol there, this integral symbol here says if you're above the x-axis, you represent a positive thing. But if you're below the x-axis, that is a negative area. All right, so for the integral sign, you're going to have cancellation, and you might even have a negative final answer. Okay, Ben asked, is this f or f prime? So this is an f prime graph. We don't have a picture of f in front of us. But we're going to use this fundamental theorem to answer part B here. It says, assuming that f of 4, not this guy, but f of 4 is equal to 2, we're going to use this information we've got up here to find f of 0. So here we go. I'm going to copy the integral that we've got here, 0 to 4 f prime of t dt. But now instead of putting a half, which we know the answer is, I'm going to apply the fundamental theorem of calculus, which is just off the top of the screen. So applying it to this particular function, remember if you're doing the integral of a derivative, you get the actual change in the original function. So this is going to be f of something minus f of something. We just got to put the right numbers in here. Which one goes first, bottom or top? It's the top one. You can look up there. It said f of b minus f of a. So then up on top is a 4, and downstairs is a 0. So that is what the fundamental theorem says. Okay, so let's start replacing these with some numbers. We've already calculated the area under the curve. The signed area is 1/2. That's what we did up above. So this thing ultimately is exactly a half. F of 4 was given in this problem as 2. F of 0, we're going to find. So either do some algebra or just look at it 1.5 or 3/2. Is that okay? Sam?
question is it says that f prime
Yes.
function is
So this function is continuous, but it's not something else. It's not differentiable. The corners, I think, if, right, you're reacting to the corners?
yeah.
Yes, and so corners are places where the graph is not differentiable. So we couldn't take a derivative of this guy at 1 or at 3. But continuous just means you can draw it without picking up your pencil.
Yeah, sorry, I got it.
No problem. Okay, so that's great. So somehow knowing, this is kind of interesting to think about, knowing where the function ended. I'm saying we're starting at 0 and ending at 4. That's all the information we have about this. So the function f, not the function picture, but the function f, it ended at f of 4 equals 2. So I've got some point. No need to draw this up here, but I'll just plot it real quick. So f of 4 is 2. This is going to be a picture of my f function, which I have not that much information about. I just know its derivative. And I know that the area underneath this derivative function, the signed area, was a half. And what that fundamental theorem tells me is something very powerful. That 1/2 just represents the actual amount that the original function changed by. So if we changed by 1/2, and we have to end up here at 2, we gained 1/2 going from 0 to 4, and you got to end at 2, then where does this function f have to start? It's got to start over here at 3/2. This is, again, the f function. It starts at 3/2, at 0, 3/2. It gains 1/2. That's what the whole area under this derivative curve tells me. It gained 1/2 in moving from 0 out to 4. And so gaining 1/2 from 3/2 lands me exactly up there at 2. You'll have lots of practice, more visual practice with this, but that's what the fundamental theorem tells you. Okay, so the group activities start on the next page. Let's see how far we can get and raise a flag if I can help.